It's recording now. Do you see a light?
I don't see a light.
Okay, but it's recording.
Okay.
It started.
Okay, good. The purpose of this talk is to go over all of Chapter 5 in one session. Now, this is going to be an overview, so I'm going to leave out many details, but the ideas are going to be the same throughout the work we do in this chapter. I'm on page 302 of your text, and we'll start off with a simple example. First of all, suppose you need to know a couple of things about the first and second derivatives. If you look on page 317, you'll see what's called the first derivative test. And what the first derivative test says is that if you have a derivative, you have the derivative function, and I'm going to put the sign of the derivative on top of the x-axis, the sign of the first derivative. Suppose you have plus, okay, the derivative is positive for all these values of x, and then all of a sudden it's 0 or does not exist, and then it becomes negative. So if you recall back to way back, we determined that where the derivative is positive greater than 0, that means the graph of the original function is increasing. Where the derivative is equal to 0, that means that the graph of the function is horizontal, the horizontal slope. So, and then on the other side, if it's negative, that means the graph of the original function is decreasing. So you have this situation of the original function going up, and then you go down. Okay? So it's just like if you're suppose you're in the back seat of a car, and you've got your eyes closed, and you feel that you're going up. You feel that the car is going up, and then the car levels off, and then the car goes down, starts going down. So you know that you have gone through an overpass or some bridge or something like that. Similarly, suppose you have another point, and here's another point where the derivative is equal to 0. Then, and on the other side of this is increasing. Then you know that, again, you're in the back seat of a car, you're going down, you level off, and you go up. You know that you've gone through an underpass or maybe a tunnel or something like that. So you know that the graph of the function is kind of like that. The original function is kind of like that. This situation right here, this situation where the derivative is equal to 0 is called a critical number. Where the derivative is equal to 0 or does not exist also. In this situation, the same thing, you have a critical number there at that point. Let's call this point A and point B. Okay, so this is called the first derivative test because this is you know the graph of the function is like this, and then it's like that. This is called a local maximum. And this is called a local minimum. Singular. Local maximum or local minimum, singular. Collectively, they're called extrema. Extrema means either a local max or local min. Now, what we're talking about is the use of the first and second derivatives, and I'll talk about the second derivative in a minute, is to find optimization problems. And an optimization problem is where something is either maximum or minimum. And it's optimal depending on what side of the table you're on. For example, you're trying to buy a car, so optimal for you is to find the minimum amount of money that you want to pay for the car, and optimal to the salesman is the maximum amount of money that you can get for the car. So it depends on which side you're on, which is optimal for one or the other. But let's get back to the sketching of curves. Now, if you look again on page 318, for all x for which the second derivative, here's a couple of little factoids that you should know. Remember, we have f prime greater than 0. This implies that the graph of f is increasing. F prime less than 0 implies that the graph of f is decreasing. And by the way, this is a double implication. It goes both ways. And f prime equals 0, of course, implies that the graph of f is momentarily, the tangent line is horizontal at that point. Now, similarly, there's something called the second derivative test. Now, when I'm working a problem later on, I'm going to put the the second derivative data below the x-axis. I put it on top of the x-axis for the first derivative. I'll put it on the bottom below the x-axis for the second derivative. But for the second derivative, wherever the second derivative is greater than 0, then that means the graph of f is concave up. Concave up. In other words, the shape is a smile. It's a smile. For all x for which the second derivative is greater than 0, you have a smiley, right? And where the second derivative is less than 0, then this implies that f is the graph of the original function is concave down, and that's going to be a frown. Now, it should be, if it's not obvious, it's kind of apparent. If you have a first derivative critical number where you're at where you're concave up, then that first derivative critical number is going to be the x-coordinate of the local minimum. And over here, where you have a critical number at a concave down area, then you know that that critical number is the x-coordinate of a local maximum. So this is called we could have used the second derivative test on this, because if you take the second derivative, I don't have an equation for this, so I can't give you a good one. But right here, let's just eyeball this. From here to here, the second derivative is going to be, this is concave down, so the second derivative is going to be minus. You don't have to put all these minuses down. You can just put 1, as long as you're clear about where the area is. Right here, the second derivative, see that smile right there? The second derivative is going to be positive, right? So, and here where it changes, right, this is the original function. Here where it changes concavity, it changes from concave down to concave up. This is called the IP, or inflection point, or point of inflection. The inflection point is where it turns around, where it changes course. So, and it's used in other areas, of course, other than in calculus. For example, our governor was doing real well for running for the Republican nomination for president until he made a boo-boo in his talk. So that was an inflection point for his run for the presidency. Everything just collapsed after that. Changed directions. So that's the idea of inflection point. Let's use this a little bit on this equation. I think I'll reset. I think I'll just move it out of the way. Okay. Let's look at sort of an example on. Go back to the original page where this is a graph on page. The original page that we started off with was just page 302. And on the bottom, figure 2, he's got the graph of a function. This is just the first derivative. He's got the graph of a function right here, okay? And the graph of the derivative of the function, y equals f prime of x. And here's a minus 1, and here's plus 1. And again, this is on the bottom of page 302, and this is y equals f prime of x. And it goes kind of like this, okay? Y equals f prime of x. And you can sketch a graph. You can't sketch the graph because you can't do it without the original equation. You have to know the y coordinates. But you can give a general overview. This guy is this is the derivative, and it's increasing until you get a minus 1. Then it's decreasing from minus 1 to plus 1. And then on the other side of this, it's decreasing. Why? Because the derivative is positive, greater than 0. So this guy changes. Right here is going to be the local. Okay, it's going to be a local maximum, right? Because it's up. Okay, and then right here, the derivative is equal to 0, and it's going to continue down until you get a little lower, right there, and then it goes up right here. So if you look on the facing page, he's got a graph of that function, a nice smooth graph because he's doing it using a computer. Again, we've already talked about the concavity on page 303. He discusses that, and we've already mentioned the second derivative test. This is called the first derivative test. If you have plus, minus, plus critical number, and then minus, and that's going to be the x-coordinate of the local max. And if it's minus, the derivative goes from minus to plus, minus to 0 to plus, then that's going to be the x-coordinate of the local min. Or if you take the second derivative and that critical number that you found in the first derivative, when you were calculating the first derivative, then you you check to see whether it's in the area of whether the second derivative is negative. And then if the second derivative is negative, then this is the x-coordinate of the local max, and this is conversely, if you're concave up, second derivative is greater than 0, this is the x-coordinate of the local minimum. Okay, so that's the first and second derivative tests, and I think I'll stop here. Okay, I'm going to work another problem in great detail on page 308. Okay, you can turn it off.